Hello, I think Rico mentioned. My name is Carson, and I'm a junior at St. Stephen's, and my level 5 project was to try to generate music using a recurrent neural networks, which are names. So I presented this project a bit while I was working on it in the past, and also I don't have a ton of time, so I'm going to go over a very brief overview of how a neural network works. So basically, think of a neural network as a function. I think most of you have probably taken math class before. It's a function, you give it an input, and it puts out an output. And the way it does it is, it's actually a fairly simple function. It takes in a bunch of numbers, it multiplies them by some other numbers, which let's call those numbers variables, and then it adds some other variables, and then produces an output. So, as you can see, here's your input, and all those lines which represent other numbers or variables that you're multiplying by. And then, so, your function will produce an output, right? And you compare that output against what it's supposed to output. And you take like the differences between what it's supposed to and what it actually did output, and you change the variables based on that. And so the goal is eventually, given an input, it will be able to predict the correct output. Now, that's just a basic dense neural network, as I have pictured here. I'm using a recurrent neural network, specifically like gated recurrent units. The difference between those is it's somewhat complicated, but to simplify, recurrent neural networks can use input from a previous time as input for the current time, and that way they can make decisions for the future based on the past, which is useful for music because music in the future should be based on the music in the past. So, a large part of my project, a large part of what I figured out was figuring out how to work with data. So I'm working with music data, and music data is a pain for a couple of reasons. The first is that it's sort of hard to get because of copyright, etc., and you have to humans have to have made it for you to have it. So that's one difficult thing. And the second thing is it's also sort of difficult to represent for neural network size data. So I'll talk about what I ended up doing for representation in a bit, but first I just want to start with one of the major things I learned, which was what's actually feasible with regards to data size. So this slide seems pretty cryptic. You've got two green squares. There's a really big one over here, and then a small one on the left. The first one is what I was trying to do at the beginning of the project. I wanted to represent my data as a square about that big, and this is to scale, by the way. So it was supposed to look like this. By the end, I realized that wasn't going to work out, especially not on my 2011 MacBook Pro. So I instead changed the dimensions. Through learning how neural network works and learning how to manipulate data, I was able to get the dimensions down to something that's like that second green square, which as you can see is a lot more manageable than the first green square. Okay, so now I'm going to briefly go over how I ended up representing my music data, because it's pretty interesting, and this is what actually a lot of the project was focusing on. I think it was maybe the most complicated part of the project. So you start with your numbers up here. You've got your list of numbers for people familiar with Python, and see 25, 27, 88, etc. So what that represents is notes playing at a given time. You can think about each number represents a note. So 25 may represent C, and then 27 would represent D, or something like that. You can think about it as notes on a piano. And then, interestingly enough, so 88 technically wouldn't be a note, it's a stop character. So think of it, it would be like, when you're writing text, it would be like the space. That means increment, one increment in time. So what this word represents is that in the first increment in time, notes 25 and 27 are playing. In the second increment in time, notes 25 and 27 are playing. In the third increment in time, notes 27 and 29 are playing, etc., etc. And so that's what it represents. And I should briefly mention that the increment in time is 1/25th of a quarter, or 1/24th of a quarter note, so it's really small, and that'll be important later for explanation of results and such. But anyway, so the first is an encoding or embedding layer. The goal is to encode what the specific name is an embedding layer. So what it does is neural networks don't like working with numbers that are bigger than 1. That's one thing to note. And also, more input is better than less input. So what an embedding thing will do is it will take that 25 and turn it into a long list of numbers between -1 and 1. So it'll take 25 and for example, turn it to -0.1, 0.2, 0.2, -0.3, etc. And in my actual network, I ended up using 200 dimensions or something like that. So it would be a list of 200 long of those that's unique to every number. So 25 would have a representation, 27 would have a representation, and so would 88, and so would all the rest of them. But they would all have a unique representation. So then I'm going to sort of hand wave you a bit over this next bit. It's the RNN, and it'll turn this data into what it thinks the next data in the set will be. So you see you've got your representation here, and the note that it predicts will be the red one. That's C. And basically the number and output it would make is that stuff below. So, and the numbers represent the probability of each note being played. So, for example, you see there's some that are 0.1 and the one that's 0.6. So Oh, that didn't make them add up to 1. They're supposed to add up to 1. But the idea is, if it's supposed to give a probabilistic output instead of a one hot encoded output, which basically means it would always choose the same note. The reason is, when you find out, once you make the model, if it always chose the note with the biggest probability, it would make the same note over and over again. And that's not very interesting music, is it? So instead, it chooses from the probability. So it would have a 10% chance of choosing the one note with 0.1, a 10% chance of choosing the other note with 0.1, and then a 60% chance of choosing the one with 0.6. And that's how it works. And that's the output it makes. And it uses that, it does that a bunch of times and makes, in succession, therefore, a bunch of music. So I think, now I'm going to just a quick technical description of the code. I was using Tensorflow for people who are familiar with this. I was using Tensorflow with Keras Functional API. The structure of the neural network was an embedding layer, a GRU, and then a time-distributed dense layer with softmax activation, categorical cross-entropy loss. By the end, going down to 0.4, and for generation, I gave it a 40% chance of using argmax and a 60% chance of using argmax and a 40% chance of taking through distribution, so it was more stable. And I think at this point I'm going to try to show my code. How do I There you go. Okay, so this is my code. It's a Jupyter notebook, and I think, well, I'll explain it now. So as I already mentioned, my 2011 MacBook Pro is not the best computer. It has some issues. So I was like, how am I going to run these complicated machine learning tasks? Well, I figured out Google Colab is a pretty cool thing. So it's basically, all of you are probably familiar with Google Drive, and you can have text files, etc. Well, you can also have Python files in Google Drive. And what's nice is that Google has free computers that they'll let you use to run your Python code. And these are fast computers, so that's really nice. So that's the reason it's in this format. But
the error is my fault, by the way.
Yeah. So this first function is my data function. Basically what this does is it gets the data. I'm not going to go over it in a lot of detail because time, but this second part right here is my neural network. So this is the model itself. You've got your input, the embedded layer, and for those who are familiar with neural networks, forgive me for labeling them LSTM and then making them GRUs. I changed that at the last minute. So then I just make the model. This is my second data function. I needed 2 of them because one of them does different things than the other. One of them was for the other data to convert it, and this one is to process the data. These are my variables. So the number of total data, that's how many data samples I had. In the end, after getting my music data and processing it and taking one that had too many notes or too few notes, I ended up with 15,509 pieces of music. Batch size is 100. That's basically, okay, so you can't fit all of the music data in memory at one time because it's a lot of data. It's 15,500 bits. So what you do is you split the data up into little bits. Batch size is 100. So you'll take 100 at a time and work on those and then do that again and again. And that way you can fit all, you can do it without crashing your computer, which is good. And this is my final bit of code. This just is essentially what actually does the work and trains the model. It'll take an input, make an output, adjust the neural network based on what the output should be, and do that over and over again until it gets to a point where I'm satisfied with it. And I guess I'll briefly mention, this code doesn't actually seem that long, but I spent a lot of time refining the neural network and refining the data. I have tons of code, maybe 10 or 20 times this code that I wrote and didn't end up using. So I think I'll speak a bit more to that in the end. And going back to the presentation, oh, no, I can play my music now. So this is the final results. I hope the sound can play, but. And what I think it could work on. So the first thing, it definitely created a sense of which notes go together. So I didn't tell it how to play chords. It learned that you should play certain notes together that sound good. And secondly, it also learned which chords go from one chord to another. I'm not very technical with my music terms, but it learned which chords flow well into other chords. As you can hear, it, for the most part, chose chords that went well together. Also, it learned rhythm somewhat. As you can see, those were sort of rhythmic and not just all over the place, which wouldn't be very impressive, except considering I'm using 1/24th of a quarter note per time step. It had to learn that I have to predict, 48 of these, or 64 of these, or whatever, which shows that it has some sort of long-term memory. But that being said, it definitely could improve its long-term memory. As you heard at the end of that bit, it was starting in a major key, and then it switched to a minor key, which was sort of a sudden shift. So it knows how, for long form things, it has rhythm sense, but not note sense, which is something it can improve on. And I think the biggest thing it can improve on is so the maximum length I can generate music is about double that, because after that it starts predicting not according to the format I made. So that's definitely something I can work on. So, and I think I'll just conclude this presentation with a discussion of what I learned, which there were a lot of things. So the first was TensorFlow, Keras Functional API, and neural network structure. So going into this, I sort of knew what they were, but I didn't really know how to use them. So I've done a lot of documentation reading, etc., on how to use all of those things. And then how to better represent and manipulate data. So I had to do a lot of working with my data on my hard drive and both with NumPy and stuff. So I had to zip files, use OS library, etc., all that stuff. And I've got some things that have sad faces by them. Web scraping and word-to-vec embedding. Those were things I didn't end up using. So I guess I'll tell a short story. I wanted to figure out how to represent my data. So I'm like, this data's complicated. What if I got violin data instead? So it would just be one note at a time. So I was like, okay, there's a website that has it, but I have to web scrape it. So I figured out how to use Tor to hide my IP address. I wrote web scraping stuff, etc. I had my program all worked out, and then the day I went to run it, they changed their policy so you can only download 20 songs a day. And as you can see, I need 15,000, so that didn't work out. And the second is word-to-vec embedding. So I was like, how can I take music and turn it into vectors? So I decided, there's a really cool thing called word-to-vec, and it'll take words and turn them into numbers based on their meaning, which is a very abstract concept, but that's really cool. But I tried doing that, and I learned that it takes a really long time. Also, if you produce something, you have to compare it to all the stuff to find notes, and that's a task that takes a really long time as the number of notes increase. And the problem is you can play multiple notes at once, so you can think that the combination of notes that can be played is a ton. Anyway, so I didn't end up getting to use either of those in my final project, but they're really cool, and I thought I'd mention them. And I think all of those feed into one thing that I learned a lot about, which is how to read, understand, and make use of documentation. All of the learning I did about TensorFlow and NumPy, a lot of it was on my own. I had to figure out how do I do this, and well, luckily, there's a lot of resources online about how to do that. But unluckily, they're not always the most easy to understand. So I learned a lot about reading documentation, how to use it, and how to tell what functions to use because of it. And then next, how to use Google Colab and Google File Stream. This is what I mentioned earlier. Google has free CPUs, GPUs, and TPUs that you can use that are fairly fast and will speed up your code. And then finally, I learned a better understanding of what is actually possible on a computer, as my green squares demonstrated, and just learned that you have to think about the limits of your computer before you start something. I think, yeah, that's it.